So my name's Ryan Good, and this is the design of an apparatus to measure leakage rates through cracks in thin metal sheets. My supervisors are Drs. Harville and Kay. So I'm just going to go over a bit of an outline here. We'll look at the objective theoretical background, some of the requirements I came up with, and how that helped me develop my design options towards my final design, some of the results I got, and how I compared these to what I was expecting, and then some possible future work. And if you'll take a look at the left here, these are steam generator tubes, and this is actually the typical manner in which they rupture. They can either be kind of short and fat ruptures or long and skinny ones, but generally they all go longitudinally. So my objectives were 3: to design an apparatus capable of measuring the leak rate through a cracked sample section. I also had to observe and record the leakage rates through these cracked, and compare these leakage rates to the size of the cracks to see if there's any sort of correlation. So a bit of a theoretical background. So basically, when we had our semester 1 apparatus, it was to figure out the force required to pull apart a thin metal sheet. And the purpose was, how would this relate to the hoop stress required to pull apart a pipe? Is there any sort of translation between that? Hoop stress is a significant force in a pipe. It's theoretically about twice as large as longitudinal stress, based on the diagram shown. And this approximation is good for thin-walled pressure vessels, which is appropriate for a steam generator tube. So that's one of the potential applications. And so what it basically boils down to is, when might these tubes rupture? Is there any way to kind of measure that based on the potential leak rate? So I have 7 design requirements. One of them is the test sample should be replaceable without changing the test segment. Obviously, you want the sample section to remain the same through all of your trials. Leakage rate from the crack must be collected and measured so you can get the leak rate. The test collection system must be in view of the operator while they're operating the device, so they can make changes accordingly based on what they see. Regular operation of the apparatus shouldn't damage any of the equipment, because then you have to start again. It wouldn't be exactly the same equipment as before. There shouldn't be any measurable leakage rate from anywhere but the test section. Obviously, you don't want to have pressure losses in your pipes from leaky connections or the affixation method. You want all of it to come out of the crack. You want that to be the single point of failure. Fluid pressure should be monitored so you can know the pressure that you're actually operating at, and the cost of equipment and everything else should be minimized. So this is how the sample is actually exposed. So basically, it's a 1-inch carbon steel pipe, and it's milled out about halfway. It's about 4 inches long. And you basically place the sample over this section, and the sample has a crack in it, and the water will pass through and then leak out of the crack. And so these are a couple different design options. So one of the first ones I had was duct tape, because haha, you can use duct tape for anything. But it actually has a lot of advantages to it. The primary function of duct tape is at a junction between 2 metal pieces to seal off the fluid flowing between it, which is exactly the same thing I'm trying to do right now, so it was pretty appropriate. The other one was having rubber fixed on there with hose clamps. This is similar to like a car radiator. You'll have a hose connected at 2 points. You do clamp the hose on to stop the fluid from leaking through. I did go with the second one initially because it would be replaceable. With duct tape, you'd have to throw the duct tape every time. The leak collection method was this. I really only had one horse in this race. Essentially, it was a plexiglass box. And you have the box, and the water would come shooting out of it, hit the walls, and get collected. It had hinges on it, or it would be over top, so once you wanted to replace the sample section, you just pop the hinges open, replace it, and then close them again. There's a funnel at the bottom, so the water would collect at the bottom, leak down, and then fall into the scale or whatever collection method. So I did come up with this conceptual design. Essentially, the box is placed over the pipes. Everything leaks out the funnel into a bowl, which is placed on a scale. And you'd measure the output of the scale to see how fast the water is increasing based on the increase in mass. Knowing the density of water, you can get the volume. And so is the current apparatus. So you can see clearly it's not a box, it's a tube. There's a few different reasons for it. One, it was free. I'd already had the hole drilled in it, so it was easier to use. But it has more advantages than that. Because there's no hinges, there's no cracks for the water to leak out if you don't really have to seal around that. You can actually just slide the tube over the pipe instead of actually opening the hinge, and you can still replace the sample section. And because of the curvature of the tube, water will naturally flow down towards the hole instead of kind of collecting at maybe the corners of a box. So it did have a lot more advantages. And you can see there's a lot more duct tape involved. This is actually a combination of both things. So you can see there's kind of a little bulge here. I know the lights are a bit bright. But basically, the rubber is placed underneath. The metal is placed on the rubber, so there's a metal to rubber seal, and then you have the duct tape placed over top. The duct tape really has the advantage where it can still apply a pressure if you put it on tightly, but it won't warp the sample. The hose clamps, when I was trying them, they would actually kind of bend the sample to get enough pressure required. So it was reduce the integrity of it. It wouldn't be as appropriate. And then after that's out of the way, this is the whole thing. It's sealed at the ends with blue Play-Doh, and it served its purpose well. It stopped the leaks from coming anywhere else but the hole in the bottom. It all gets drained into a bucket. The bucket's sitting on a scale. The scale outputs on a stool sitting further away, so no water gets in the scale. You don't want to damage anything. That's why the scale's underneath the garbage bag. And then there is a pressure gauge on the side, so you can measure it. Originally, it was intended so there'd be pressure taps on both sides, but the flange that it's attached to is impossible to get apart. This flange actually only separated from a section by a Wayne Leppett using a blowtorch to expand it and get the pipes apart, so that one, he said it wasn't possible. So this will be an actual video of the leak rate. It's short, but watch carefully. Okay, so a couple things there. That's actually way more water than I thought it would be. It's only going at about 50 kilopascals or less by the time it reaches that section, but the water bursts out right away. So it was actually surprised me the first time I saw it. So I did a bunch of tests and I plotted all my data. So essentially this is the leak rate in liters per second across the total flow area of the crack. And it kind of looks like there's no correlation at all. R squared is basically 0. So there's kind of some problematic data. And it started in these red ones here. So when I started doing the samples, I started with the largest sample. I saw those 3 points grouped together and I thought, okay, great, that's appropriate. And then I got to these ones and I kind of wondered what was going on. It wasn't actually part of my design. It was part of the loop I used. So it's a bit difficult to see, but there's some red circles here and here. So basically in the loop, it's a drainable loop. That's why there's all that water in the bucket. So for the water to go through the system and pump out the air once the system had been drained, it goes up that pipe there, connects to the hose, and will drain down to the bottom. And that's how you get the air out of the system and get water flowing through it. When I was using the 3-inch samples, there was enough water flowing through it that I didn't really notice the difference. But you can actually see on that previous video, there's a little bit where the water kind of dropped and spurted. That's where there was a passage of air going through it, and the water would pass through to the end of the bucket. When I turned to the 2.5-inch sample, the crack was small enough that the leak rate would actually be 0 for as much as 5-10 seconds at a time, and the water was bypassing it entirely and going to the drainage section. Because the drainage section is at a lower point in gravity, it was more advantageous for the water to go down and drain there than actually come out of the crack. So once I sealed off the drainage hose, everything was working fine. And then I got this correlation. I know it seems kind of obvious. If you got a bigger crack, more water is going to come out of it. But I think what the interesting thing is that the crack on the right is actually more than 5 times the size of the crack on the left, but the leak rate only increases about 50%. So if you were to use this to kind of detect what the size of your crack might be, a small increase in the leak rate might actually be more dire consequences than you might anticipate. So it's worth looking into. So just in concluding remarks, I did design an apparatus capable of measuring the leak rate through my crack sample section. I observed and reported the leak rate through the manufactured crack, and then I compared the leakage rates to the size of the cracks to see if I could kind of get some results from that. And I did the whole thing for less than $30 in procurement. If I was to do it again and focus on the accuracy of the results, I'd probably spend some money to get some more accurate stuff. But for the purposes of validating the design, which is the point of capstone, I think it did a good job. So some possible things to do in the future. Now, I might do a different loop for more pressure measurement points. Obviously, I had one of the 2 taps at the start, but it wasn't feasible with the materials at hand. I might modify the leakage and bucket assembly. I definitely wouldn't use Play-Doh again because it kind of mixes with the water and gets stuck to your hands and everything. But most importantly, crack manufacturing method. My cracks are made with an X-Acto knife and they're wide, and they're perfect for validating the design because I was able to get so much flow to them. But if you want to look at more real-world applications, cracks don't really get cut with an X-Acto knife like that. So you might want to look at some different techniques to kind of modify the design there. So I'd just like to acknowledge Dr. Harville and Dr. Kay for their guidance and support. Members of the Nuclear Design Lab, Jeffrey, Abjad, and Adam, for their valuable discussions. I'd like to thank Taylor, Tudor, and Rob for their help with all the project and Thesis I. Sharma, Robert, and Bradley for helping out with the equipment and getting access to the lab and everything. Wayne Leppett for his work on the flange, because without him, I might not have been able to do the project at all. Miro for helping with the testing process because I can't be trusted in the lab by myself. And Molten Salt Group for letting me into the downstairs lab because as of April 9th, I still don't have access. Any questions?
Questions?
Yeah.
Can you go back to your correlation between like the crack size and the
This
flow
one?
rate? Yeah, that one.
Yeah.
So you said that as the crack gets larger, the actual increase in leak rate is only a certain amount. Why do you think that's so?
I think it kind of depends on the formation of the cracks too. Again, as these are cut with an X-Acto knife, I wouldn't maybe call them cracks so much as kind of very long, thin holes, because basically they have a certain minimum thickness of the blade of the X-Acto knife, and they're a little bit thick. But I think it's dependent on a lot more than just the crack flow area. It's probably dependent on the pressure it's operating at too. And after a certain size increase of the crack, it just might not actually add to it. I did choose a logarithmic function, so it kind of would give you the impression that it would level off at the end, and the increase here might be more stark. Again, more testing might be required to validate any sort of relationship there. Europe?
What is the approximate percentage of uncertainty are you having with the entire experiment? Just ballpark estimate.
It's kind of difficult to say. Certainly the measurement leak rate would be the biggest source of error, because essentially the method is the response of the scale. So it's a digital scale. The output was on that cord connected to that machine. So basically with the testing process, I recorded the scale moving up while it was leaking. So I mean, after the initial hit of water, it would be a constant rate. And so basically I opened it up in VLC Media Player and watched the timestamp, took a bunch of different measurement points. One of the options I did explore was using a flow meter instead of this. It might give you a more accurate response time in the moment, but again, it would require a lot more precise instrumentation than simply a hole at the bottom of the thing. I might have to connect it to a pipe or hose and get the flow meter and ensure it works. So for the purposes of the design, it was better just to kind of go with the scale measurement method. Dave?
You said this could be used in the nuclear industry for steam jet pipes, correct?
I said that's one of the potential applications.
Yes. So, in your opinion, do you have any other purposes for this setup outside of the nuclear industry?
I haven't really given it a lot of thought, but of course, cracks in pipes applied a lot more than the nuclear industry. It could be used for any industry that just use pipes. I don't know if it would really have an application going towards like a consumer-based things, pipes in the home.
Has lots, but someone's got to pay.
Yeah.
So your cracks are slits in duct tape, is that right?
The cracks are slits in metal. Let's go back to this. I'll turn the light off maybe. So it's a little more clear. So this is a copper sample, and this is the duct tape over it. So essentially there's the milled out section of that carbon steel pipe. The copper is placed over the milled out section, and then it's taped at the edges to ensure that all the water leaks through the crack and not through the sides of the milled out section.
So how stiff is that, the material around the crack? It's not a pipe, it's a piece of sheet.
Yeah, it's a piece of sheet. It's about a little less than a millimeter thick, yeah. But it is fairly rigid. I mean, if you really took a hammer to it, you could obviously dent it pretty good. But for the test, it does not actually move during testing. I could go back to the video. The water doesn't, but higher pressure applications would call for a thicker material with more strength.
Okay, so as the side length of the crack changes, you don't notice whether the section actually bulges a little bit or not.
So based on the size of the roll we have is probably about this big, and obviously it's wrapped around a 1-inch pipe. So when I was measuring the size of the cracks, I measured it based on when it was wrapped around a 1-inch pipe, and actually the crack does bulge